Really think about it for a second. You get this result, the single number, and it could be the basis for some pretty major health decisions. So your ability to trust that number, it's not just a feeling, it's built on an incredible foundation of intense, rigorous scientific validation. But what does that process actually look like?
So that's what this is all about. We're going to follow the journey of a brand new lab test from start to finish. We're going to see exactly how scientists prove that a test is reliable and accurate before it's ever used to diagnose a real patient. And to make this super concrete, we're going to use a case study that comes straight out of the lab's playbook, a new way to test for blood glucose. Let's say the lab just got a new machine. They have to answer one absolutely critical question. Is this new gadget accurate enough to be trusted with your health?
But before we can even begin to answer that, we have to get really specific. Because in science, words like accurate have very precise meanings. So when a scientist in a lab coat says a test is accurate, what do they really mean? At its core, accuracy is just how close a test's result gets to the actual, true, correct value. Simple enough, right? And any difference from that true value, well, that's called inaccuracy. Or, if you want to get technical, it's called systematic error or bias. You can think of it as a consistent, predictable error. Our whole job here is to measure that error and figure out if it's small enough to be acceptable.
Okay, so how do you actually check it? Well, labs have a couple of ways to do this. They can compare the new test against the absolute gold standard in the field. That's called a reference method. Or, and this is way more common, if a lab is just upgrading its gear, they'll use a comparative method. They basically put the new machine in a head-to-head battle against the old trusted one, and that's exactly the path we're taking with our glucose test.
All right, so this is where the rubber meets the road. We're getting into the hands-on part of the investigation, the experiment itself. And it's basically a super meticulous head-to-head competition between the old way and the new way.
Now, this is what I find so cool, the sheer level of detail here. First, you need at least 40 different patient samples. And this is key. You can't just use normal results. You need samples that cover the entire spectrum, from really low values to really high ones. Then you test every single sample on both machines, and you have to do it within 4 hours so the sample itself doesn't change. Oh, and this isn't just a one-day thing. You spread it out over at least 5 days to prove the results are consistent, day in and day out.
Okay, the experiment's done. We've got a huge pile of data. Now comes the part that separates a guess from actual proof, the statistical analysis. This is where we dig in and find the truth. Now, a lot of people hear correlation and they think, job done. You know, you run the numbers, you get a super high correlation, like 0.99. You'd think the test has to be fantastic, right? The two methods are moving in perfect sync. But that is a classic trap. And here's why. This is such a critical point. Correlation does not measure accuracy. Think about it. A new machine could be consistently reading, say, 10 points lower than the old one on every single sample. It would have a nearly perfect correlation, but it would also be consistently wrong. That's why we need a much smarter tool. And that better tool is something called regression analysis. This is the real hero of our story. It doesn't just tell us if the two methods are in sync, it gives us the specific mathematical relationship between them. It gives us the slope and the y-intercept. And with those two little numbers, we can finally calculate the actual quantifiable systematic error. So we've collected the data, we've picked the right statistical tool, all the pieces are in place. It is time for the final calculation. It's time to deliver the verdict on our new glucose test. So here's what our regression analysis spit out. We've got a slope of 0.96 and a y-intercept of 2.36. Now we need to focus on a value that really matters to doctors, a critical concentration. For glucose, that's 126 milligrams per deciliter. It's a key number for diagnosing diabetes. And finally, the government regulations, CLIA, say the maximum error allowed for this test is 10%, which is 12.6 milligrams per deciliter. That's our line in the sand. Okay, first up, we use that handy formula from our regression to predict what our new machine would actually read if the sample was exactly 126. So we just plug in our numbers. Y equals our slope, 0.96, times 126, plus our y-intercept, 2.36. And boom, the answer is 123.3. So that's what our new test is expected to say when the true value is 126. We can already see it's reading a little bit lower, but is it too low? Is it an acceptable difference?
To find out, we just need to calculate the systematic error. And it's really simple. We just take the true critical value, 126, and subtract the value our new machine gave us, 123.3. And there it is, 2.7 milligrams per deciliter. That is the number we have been working for this whole time. That is the systematic error, the consistent, predictable inaccuracy of our new glucose test. Now for the final showdown. We take the error that we just calculated and we put it right next to that maximum allowable error, our line in the sand. And as you can see, it's not even close. Our calculated error of 2.7 is way, way smaller than the allowable error of 12.6. The verdict is in. The new method passes with flying colors. Its accuracy is officially and mathematically acceptable for doctors to use.
Imagine you're building a skyscraper. You wouldn't just start stacking floors without first making sure the foundation is solid, right? You'd test everything, from the ground floor all the way to the top. Well, in a clinical lab, the same exact principle applies. Before we can trust a single patient result, we have to build this kind of scaffold of certainty around our instruments. Today, we're going to dive into how labs verify their reportable range and linearity, which is how we make sure every single result we issue is both safe and accurate.
So here's our game plan. We'll start by defining what a measurement range really is. Then we'll walk through the actual step-by-step verification protocol. After that, we'll look at 3 different ways to think about linearity, figure out how to budget for acceptable error, and then pull it all together to make that final pass or fail call. We'll wrap things up by talking about who's ultimately responsible for this whole process. It's a straight shot from theory to practice, so let's jump right in.
Okay, first things first. Before you can measure anything reliably, you have to know the limits of your ruler. Section 1 is all about defining our field of play, the measurement range. So let's frame this with a really important question. How wide is your window of accuracy? You see, every lab test has a specific window where its results are completely trustworthy. Outside that window, things get a little blurry, and that's where patient care could be at risk. Our job is to very precisely define and verify the edges of that window. The big official term for this window is the reportable range. This is the entire span of results from the very lowest to the very highest value that the lab is willing to stand behind. If a result is in this range, the lab is basically certifying its accuracy. It's their promise of quality to the doctor and the patient. Now, the reportable range is built on something called the Analytical Measurement Range, or AMR. Just think of the AMR as the instrument's natural talent. It's the range of values it can measure directly from a sample, no tricks, no extra steps. This is the out-of-the-box performance we're testing. But, what happens when a patient's result is critically high, like way outside that core AMR? You can't just tell the doctor it's high, they need a number. And that's where the clinical reportable range comes into play. It takes the AMR and extends it by using validated procedures like dilutions, which lets the lab accurately measure samples that would otherwise be way off the charts. So, just to recap and make it super simple, the AMR is what the instrument can handle all by itself. The clinical reportable range is the total extended range the lab can confidently report to a doctor, and that includes any of those special dilutions. This slide sums that relationship up perfectly.
Okay, we've got our definitions straight, but how do we actually do this in the lab? Let's move on to Section 2 and walk through the verification protocol. This is really the how-to guide for building our scaffold of certainty.
So, to run a good verification, you need the right stuff. You've got to use at least 3 levels of material, a low, a mid, and a high. And here's the most important part. You absolutely have to pick samples that are near the upper and lower edges of your range. Why? Because you have to challenge the boundaries to know if they're real. That's where things are most likely to go wrong. You can use commercial kits, your daily QC material, or even patient samples to do this.
Here's a pretty standard protocol based on guidelines from CLSI. It suggests you take 5 samples that cover your whole range, then you measure each one twice. And you don't just do it once. You repeat that process over 3 to 5 different runs to make sure your data is solid. The final step is pretty straightforward. You compare the average result you got with the known true value. If that difference, what we call bias, is smaller than your preset error limit, then congratulations, the test passes. And listen, verification is not a one-and-done deal. It's a process of constant watchfulness. CAP requires you to do it at least every 6 months, but you also have to re-verify anytime something important changes. You get a new batch of reagents, the instrument has a major repair, or even if your daily QC data starts to look a little weird.
Now let's zoom in on a really key concept in all of this: linearity. Put simply, linearity just means that if you double the amount of something you're measuring, the instrument's results should also double. It's all about making sure you get a proportional, predictable, straight-line response across the entire range.
Well, it turns out there's more than one way to define linearity. The traditional way is to just eyeball a graph and decide if it looks straight. As you can imagine, that's pretty subjective. The statistical approach is more rigorous. It uses things like p-values to see if the data is statistically different from a perfect line. But the one that really matters for patient care is clinical linearity. It asks the most practical question: can we draw a straight line that stays within a medically acceptable error margin of every single one of our data points? That's the standard that actually impacts decisions.
So, to check for clinical linearity, we use a few key tools. We calculate a best fit line that runs through our data points. In a perfect world, that line would have a slope of exactly 1 and an intercept of 0. We also look at the residuals, which is just a fancy term for the distance between each data point and that best fit line. The size of those residuals tells us exactly how much error we have at every level we tested.
Speaking of error, you can never completely get rid of it. The goal is to manage it. And that brings us to Section 4, creating a budget for allowable error. Seriously, just like a financial budget, this defines exactly how much error we can spend and still feel confident that we're producing a medically reliable result. The cornerstone of our budget is the allowable total error, or TEA. This is a huge deal. It's the lab's official written-down policy that states the absolute maximum error allowed for a test before it could possibly cause a doctor to make the wrong call. Every single pass/field decision we make flows directly from this one number. And as this chart shows, we don't just use that TEA as one big lump sum. We're smarter than that. We allocate it. A really common rule of thumb is to dedicate no more than half of your total budget to systematic error, or bias, and no more than a quarter of the budget goes to random error, or imprecision. This strategy is great because it forces us to control both accuracy and precision, and it still leaves us a nice little safety margin. Okay, deep breath. We've defined our range, we've run our experiment, and we've set our error budget. Now it's time for the moment of truth. Section 5, making the pass or fail call. This is where we bring everything together, our data and our rules, for one final objective decision.
This table right here is basically the algorithm that puts it all together. It's a 4-part checklist. First, for accuracy to pass, our measured average for a sample has to be within that systematic error budget. Second, for linearity, a straight line has to fit through all our data points without ever going outside that same error budget. Third, for precision, the wobble in our data can't be bigger than our random error budget. And finally, for the whole reportable range to pass, our highest and lowest test points have to be accurate themselves. It's a really thorough check that leads to a confident result.
So we've covered the what and the how, but to really finish the story, we have to talk about the who. Who is ultimately on the hook for making sure all of this is done and done right? And the answer couldn't be clearer. It's the laboratory director. This quote makes the point that defining these rules and making sure these procedures are followed isn't just a technical task. It is a core responsibility of leadership. It's a cornerstone of the lab's commitment to quality and patient safety, and it's overseen from the very top.